This micro-credential deals with aquaculture basics and consists of 5 targeted skills. This targeted skill deals with aquaculture water quality. Aquaculture water quality is different for each species. It must be monitored in order to ensure optimum growth and health for each species in an aquaculture environment. Water quality parameters are monitored regularly, including temperature, dissolved air, pH, carbon dioxide, chlorides, and salinity. Alkalinity, hardness, and other parameters are relatively stable, but dissolved oxygen levels and pH can fluctuate on a daily basis. Establishing a standard water testing protocol is crucial for any aquaculture operation. An operator must be familiar with the tolerance ranges for a given species. Temperature affects all biological and chemical processes within an aquaculture operation. The temperature of the water can be adjusted by fish moving to cooler or warmer waters. Each species has an optimal temperature range or preferred temperature where they grow best and are affected by temperatures that are above or below the optimum. Temperature can determine what level of dissolved oxygen is safe for the organism. As temperature drops, oxygen vaporization increases. The dissolved oxygen, DO, in ponds can fluctuate dramatically within a 24-hour period. In a culture system, the DO must be kept above levels that are considered to be stressful for fish. Cold water fish, like salmon and trout, can tolerate higher DO concentrations. On the other hand, warm water fish, like catfish and tilapia, prefer lower DO concentrations. As a general rule, DO levels should not exceed 3 parts per million, or ppm, for cold water fish, and above 5 ppm for warm water fish. Long-term exposure to non-lethal, low levels DO can cause chronic stress in fish. Aeration and oxygenation are required for intensive fish production systems, such as ponds, cages, or flow-throughs, to keep DO levels at a safe level. The pH of water is determined by concentration of acids and bases in it. A pH below 7 is acidic. A pH above 7 is alkaline. The pH of the water should be between 6 and 9. This is where fish will thrive and survive. Fish growth is reduced if pH readings fall outside of this range. Mortality can occur at pH values below 4.5 and above 10. Alkalinity measures the buffering capacity of culture water in terms of parts per million calcium, expressed as ppm calcium. It refers to carbonate or bicarbonate ions dissolved in water. As carbon dioxide levels fluctuate, pH levels will shift accordingly. In an ecosystem with poor buffering capacities, such as ponds with photosynthetic activity, this can cause carbon dioxide to accelerate even further. The range of alkalinity that is suitable for ponds is between 20 and 300 ppm. Alkalinity in ponds remains relatively constant. But when necessary, it can be increased with agricultural limestone or sodium bicarbonate. Carbon dioxide in high concentrations can cause fish to lose their equilibrium, become disoriented, and even die. It can be reduced to acceptable levels by testing groundwater and aerating when necessary. Carbon dioxide levels in large fish tanks or recirculating systems must be managed carefully for carbon dioxide levels to remain acceptable. Techniques include careful planning, aeration, oxygenation, and buffering. Municipal water supplies usually use chlorine at concentrations between 1 ppm and 2 ppm to combat bacteria. If municipal water is used to grow fish, residual chloride must be removed through either aeration or chemical treatments, such as sodium thiosulfate or activated charcoal. Concentrations as low as 0.02 ppm can still stress fish. Salinity is the total concentration of dissolved salt in water. Fish have a wide range of tolerance to salinity. Osmoregulation is the maintenance by an organism of an internal balance between water and dissolved materials. Salinity affects not only osmoregulation, but also the concentration of ammonia. Ammonia is the principal nitrogenous waste secreted by most fish and aquatic organisms. Total ammonia nitrogen, or TAN, is determined using analytical methods. The amount of TAN in ionized or unionized forms varies with temperature and pH. As pH and temperature increase, the amount of TAN in toxic unionized forms increases. Fish that are continuously exposed to unionized TAN at levels greater than 0.02 ppm may show reduced growth and increased susceptibility to disease. Ammonia and other metabolic wastes are gradually removed from water by natural processes or by biological filters in recirculating water systems. Ammonia from fish wastes can be detoxified using bacteria and aquatic plants that convert it to nitrite and then nitrate. Some fish are also able to tolerate levels up to several hundred ppm in their environment. Achieving effective ammonia detoxification may require maintaining an ideal pH range between 7 and 9 and a temperature between 75 and 85 degrees Fahrenheit for best results. Temperature, dissolved air, ammonia nitrite, and pH should all be monitored daily. Water clarity, hardness, and alkalinity should be monitored regularly, perhaps once or twice weekly. Measuring new sources of metabolic wastes may require more frequent measurements to assess salinity, iron, and chlorine content, so that corrective measures can be implemented in advance of planning stages. Carbon dioxide levels should be tested when first using groundwater sources, as well as on an ongoing basis in recirculating systems. Water monitoring should occur at a standard depth and time, regardless of frequency, in order for successful aquaculture cultivation.